we're advocating the simple systems. And because there are so many different names for these things, I just wanted to show some of the systems that we talk about as an introduction here. The terminology that I'll be using primarily is what's in the ASHRAE handbook. It's in the applications handbook. There's a geothermal chapter, and so there's some nomenclature there. So we use the term ground source heat pumps as the overriding topic of the classification. They're also called geothermal heat pumps, geo-exchange. Now, the first slide I've got up there is what we refer to in the U.S. as ground-coupled heat pumps, also called closed-loop geothermal, and a variety of other things. But you can see there's these closed-loop systems or ground-coupled systems will be the focus of the presentation because they're seem to be more widely used. In residential, you have the systems with, and light commercial, a trenched horizontal width is at least 5 feet or 1.5 meters in depth below grade. Of course, the deeper you go, the better off you are. There's also these horizontally bored loops where they go down typically about 5, 10, and 15 meters sort of in parallel to get better access to the soil, which is at a better temperature and usually at a higher conductivity. But the overwhelming type of system used in commercial buildings in the U.S. is the vertical for the closed loop, and typically the depths are 200 to 300 feet, or I could say 60 to 90 meters. It is possible to go deeper, but at this time urge caution when going much deeper than that. There's just not a lot of information about the issues with deeper loops. Say more original system, which is the groundwater heat pump systems, is also a good option if you have access to groundwater. It's also called open loop geothermal, and some of the closed loop purists might call it a pump and dump in a derogatory term, but it's basically a set of wells, or maybe one well that's discharged to the surface somewhere. And the heat pumps and the ground loop are isolated by typically a plate heat exchanger of some kind. The third main group is the surface water systems, also called pond loops, lake loops, ocean loops. Most of the systems we see in the U.S. are the high-density polyethylene loops, but there's also a few manufacturers that make plate heat exchangers that they put in the lakes. We do have open loop systems in surface water, but you have to be real careful there because if you're in heating, in all but a few locations, the exit temperature of the water leaving the heat exchanger will be close to freezing. Okay, so the main issue here is what HVAC system is best for the ground coupled heat pumps. Would we use the simple system, which I've laid out here, which is basically a loop that's tied together where you have, in this case, about 10 heat pumps, and each heat pump has a small circulator pump that is activated when the heat pump compressor comes on. And I've got those check valves in there, and what that does is prevents the water from backing through a heat pump when it's off rather than going to the ground loop. So this is one of the many simple systems that we looked at in the survey. And I won't make any bones about this. I have a hard time accepting why people will do this, but there are a lot of people going to, in this case, what's called a ground source heat pump system hooked to something that's quite popular in larger buildings in the U.S. Is variable air volume chill water systems, where you have either a chiller, a reversible chiller, or water-to-water heat pumps hooked to air handlers, and the air handlers, of course, hooked to variable speed fans and terminals out in the field. And in the terminals, you of course regulate the conditions by varying the flow rather than turning the machines and all on and off, and you'll see there a good number of items in that system. But it's we see more and more people doing this. Now, so how are we going to tell the difference here? Which one's the best? Can we use modeling? I think modeling, in my opinion, is a very, very, very difficult thing to do correctly. You have to have a lot of information that but I think a lot of people just do the modeling in a hurry to, you know, in this country to get whatever benefits, lead rating or something to do that. So you can see this is a building we worked on that had a LEED Platinum rating. It had chill water VAV ground coupled heat pump system and under air distribution, and you can see the models. What the monthly usage was quite a bit more than the projected, and this is total energy. It's not the HVAC energy, so you can see it was sort of way off. Now, in the U.S. currently, there's not a lot. There are some people requiring that you demonstrate the performance of a building in terms of your energy bills, but in the U.S. there's not much going to happen to you if your model is way off and you don't get it. I understand in the EU and your building energy performance is known in public buildings, and hopefully the U.S. will catch up and start to emphasize actual performance in modeling. Now, one of the things is I kind of like to go back to calculations. I'm an engineer, and you know, I've written computer programs, so I know you can't always trust them. But when I sit down and look and compare this complex system, chill water VAV, with just a simple water-to-air heat pump system, there's a lot of stuff in that thing. And when you look at the system efficiency, and of course we have these conflicting units, but if you look at this, you have a chiller, which has the same kW per ton as these water-to-air heat pumps. It's a screw chiller. So we have in the complex system, we have the air handler fans, we have the fans in the VAV terminals, we have return fans, and these are the chill water pumps. Okay. Now these things not only pull a lot of energy, but they also distribute heat to the building. Okay, so you can see I'm taking all those kW right there, that's essentially building heat that robs from the chilling capacity, and I'm adding, deducting them from the capacity of the chiller itself, which in the U.S. this is 168 tons, which is 590 kW of cooling before you deduct the heat. So in this case, we'll lose from 168 tons to 142 tons because of that heat, which goes from 590 kW thermal to 500. So it's quite a loss, and then quite a few power input requirements. So you can see we use this term kW per ton, which I convert to EER, which is converted to COP of 2.2, which is rather low for something you paid a lot of money for. Where on the other hand, all we have in the ground source is a pump, fans, and the heat pumps themselves, and we're losing 18 kW in terms of heat. So when we put all those together, we have 0.9 kW per ton and an EER of 13.4, system COP of 3.9. Now this is at full load conditions, so the seasonal efficiency will be slightly better. But there's a lot of stuff in here that creates heat. Now, when we look at what's in the U.S. called the CIBSE, Commercial Building Energy Consumption Survey, and this is for all types of systems. And what I've got up here is a term we use, thousands of BTUs per square foot per year. And in the general population of HVAC systems, you can see that the smaller, simpler systems use less energy than some of the more advanced ones. Chill water, those with variable air volumes, you can see the simpler systems here, even room air conditioners using less than these more expensive chill water systems. Okay, so let's see. In order to just go further, we wanted to look at this. We had a project sponsored by the Electric Power Research Institute and some Southern Utilities, Southern Company and Tennessee Valley, and they have permitted the results of this to be put on my website there. So you can go to my website, and there's 7 articles that were appeared in the ASHRAE Journal showing the results of this thing. In the U.S., probably the most common type of rating system that uses the actual energy consumption is our Energy Star rating from the Environmental Protection Agency. And what they do is they take the CIBSE data and massage it, and basically they have a record of how well a building does, and it's corrected. The performance of the buildings are corrected. You know, offices are compared to offices, schools are compared to other schools, and there are typically 6 to 10 items that they found to be more important with the buildings where they adjust the load, which of course would be occupied hours, computers, number of people, those sorts of things. In schools, it would be a number of walk-in coolers would be added, the things that matter in terms. So they massage that and they give you a rating. And this particular building, this elementary school, got an Energy Star rating of 84, which means when it's corrected, it's better than 84% of the buildings, similar buildings. And in order to get a rating, a plaque, or used to give you a plaque, but now they give you a letter as an Energy Star building, you have to make 75 or better. So that's our rating system. And when we did the buildings, we did about 40 ground source heat pump buildings where we surveyed. We got water temperatures, loop temperatures, energy use, descriptions of the systems, and of course when you do the Energy Star rating, you have to get the occupancy and the number of students and number of occupants, the number of computers, and those sorts of things. So you can see the ground source heat pumps. There's a lot of them up here, above 90, okay, but there's a lot of ones down here that were actually worse than average buildings. And one of the things that's interesting is all of these 90s were done by 3 engineering firms, which in my opinion that also makes a big difference, is the quality of the engineer. So this is for all types of ground source heat pump buildings that we surveyed in the field. Now let's look at the central loop systems that we mentioned earlier, but typically you'll have this central multi-circuit ground loop. You'll come in the, sometimes they'll have a vault out here, underground vault, where they manifold these circuits off so that they can be flushed and purged individually. And typically we'll have central pumps. Often you'll have heat pumps in the zones, but as I mentioned to you earlier, people are now beginning to use central chillers with VAV terminals or fan coils in the zone. So that's what we refer to as a central ground loop heat pump system. And you can see here's how it laid out. There were 3 systems with constant speed ground loop pumps, and the rest here you see were variable speed drives. So this is the central systems, and you can see that really, on an average, they were about average, and the owners spent quite a bit more for putting in a ground loop, and they got average results. We looked at 2 chill water VAV ground source heat pump systems, and you can see there were 20s, okay? And people were surprised at that, and I just say, well, go back and look at the calculation similar to the one we did on the previous slide where we got the system COP. So these fans in these systems are using lots of energy. So it was not surprising to me that they didn't do too well. Now, one of my associates is a big fan of what's called a one-pipe system, which is relatively simple. And when you first look at it, say, well, it'll never work, but it seems to do quite well. We'll see. So basically, you have a single loop, not 2 pipes, running around the building. And when a heat pump wants cooling, or heating, this little circulator pump right here will come on, and it will pull water out of this continuously circulating loop and either reject or absorb heat from the loop and then put it back in the same pipe. Okay, and then it goes out into the loop field where it is distributed to a conventional two-pipe system. Okay, and as I might say, this typically you might have one loop in the entire building, but oftentimes you might have multiple loops in the building in the one pipe system. Okay, now here we had 6 of these surveyed, and you can see they all but one scored over a 90. Okay, Energy Star. The one that didn't get the 90 was an 82, I believe, but it was a school that was built in 1938. So you see the one pipe systems did quite well. Now, the more residential type system is what I refer to as the unitary ground source heat pump system, where you have individual loops, a little on-off circulator pump, pumping to loops just outside, in these cases, the classrooms. Okay, and you see they did very, very, very well. Okay, they were 95 to 100. This particular school district where we did all these ratings actually had 4 systems out of 31 that scored a 100 Energy Star, which is quite outstanding. We also have a variation of the central loop and the individual loops called what I call a common loop, where you have a central loop over here, and as I mentioned to you earlier, you have several heat pumps on that loop with a circulator pump that comes on and off and a check valve. So these were what we refer to as a common loop. We looked at 5 of those. We had one that was operated very poorly, one that got a 97, and then these 3 here did quite well, but they were in buildings that were only partially served by ground source heat pumps. So these 2 did manage to get Energy Star, even though you can see the entire building was served by ground source heat pumps, and this one only 29% of the building was served by ground source heat pumps. So it's hard to sort out how well they did, but they did seem to do quite well. One of the things we looked at is the impact of the ground heat exchanger length. So most of the high scores were in this range in the U.S. of between 200 and 225 feet per ton, and that is a number that's normalized to the average ground temperatures of the site. So it was 63. So typically when we renormalize that in an area where the earth might be 55 degrees, that length would go down a bit to say maybe somewhere in 180 or so. If it was in warmer temperatures, some of the loops were up to 250 feet per ton. And up here at the top, you see I've got the metric equivalence, which is an inverse. So typically, you might see optimum around 60 watts per meter in many parts of Europe. Another thing, a lot of times these buildings had an excess amount of outside air, so that affected the Energy Star rating when we had equipment with very large outside air distribution systems. Pump power, some effect. I thought it would be more than this, but you can see the Energy Star rating went up with the pump power, which in this case we used the horsepower of the pump per 100 tons. So some effect there with the smaller. Now here's the one I get the most aggravation with. In fact, ASHRAE asked me to write an extra paper to explain why this happens, but you can see the buildings with the building automation systems had an average Energy Star rating of 61, while the ones with thermostats had an Energy Star rating of 80, even though we had one hotel with a 1 there that kind of skewed everything. But also, you might imagine that the buildings with control were also typically tended to be the central systems, which didn't score too well. So it's hard to sort out if it was because of the central system being less than what you want it to be, or is it because of the control system. And here's one of the things that we discovered is that there were 14 systems, central systems with a variable speed drive, and only one worked as intended. You can see here, this particular one, the drive was running right at 60 hertz the entire time. You see the differential temperatures should be you know, about 10 degrees, 8 degrees, but you can see at night it just wasn't regulated. So only 1 out of 14, and we found a lot of stuff in some of the loops like this, especially schools where they don't tend to have as good a maintenance programs. Another big issue with ground source heat pumps is that there's colleagues going around saying that these ground source heat pumps, if there's an imbalance between heating and cooling, especially if there's more cooling hours, which tends to be the case in commercial buildings, even in the South, I mean even in the North in the U.S., that the ground loop will overheat and you'll have to abandon it. Well, we did this plot here. Not sure it's the best way to show it, but basically it's the years of operation versus the approach temperature, which means the difference in the temperature of the ground as you undisturbed ground, and the average ground loop temperature in the summer, the maximum. Okay, so you can see there's actually the older loops were not as hot. These loops up here, the main reason we saw that the loops were hot was because they're just too short or undersized, and oftentimes not finished very well. They didn't do a good job of making contact between the ground heat exchanger. Now this is mainly for cooling. I wouldn't want to project what happens if you have many more hours of heating. I am from Alabama, so I don't have as much information as say folks from up in Canada or colder climates. So I really feel like we need more data to establish what these limits are, because there is some effect of ground temperature change. So I think we need to look more deeply at that. The other thing I thought is our standards are all written like the comfort standards and the air quality standards are written based on how 80% of the people in the building find in conditions acceptable, whether it be for the outside air or the acoustics or whatever. So we distributed these forms, which are very similar to the forms that the students used to rate professors with. So we've got several different things that we looked at in terms of the temperature, the air quality, acoustics, the lighting, and the responsiveness of the to maintenance issues, and the ability to adjust the thermostats. And I think that last one was the one that set people off the most. So it didn't really seem to have a strong correlation between Energy Star and comfort. You see a lot of folks here were not comfortable with the temperature, and that often correlated to the amount of outside air. So no strong correlation, but you see average above 3, which indicates that found conditions acceptable. Air quality was another issue. Looked like we had plenty of lighting in these buildings. There was almost people up to 4, which is satisfied. Slight increase of air quality with higher Energy Star score. The only decline we did have is with the acoustics. So some of these machines that got high Energy Star scores are very close to the occupants, and so there was a slight decline in that regard. And the maintenance and controllability, as you can see, was the real issue with most people. They were not happy with their ability to control the systems. You can see this is actually a decline with date in the 2 items of satisfaction with the ability to control. And of course the building automation system scored below a 3, and the newer they are, the more unhappy people tended to be. Whereas with thermostats, they had the same trend, but not as low a number. We also surveyed the equipment people, and here's the kind of stuff they like. Top left here, this is a unit where you can simply disconnect the water to air heat pump from its cabinet, remove it, service it, and put another one back in. They were thrilled, the service people were really thrilled with this kind of stuff where you have equipment that's not all jammed in there. So these are classroom units here. And then this is a unit with a it's fairly accessible all around in an equipment room. So they tend to like those things. What they don't like is these things. This is a 2-speed heat pump with a circuit board spaghetti bowl here. And you might imagine we surveyed, there were in the U.S. approximately each technician had to service 5 buildings, and they don't really like, you might have 5 different manufacturers with 5 different circuit boards, and this is a nightmare. Overhead installation of heat pumps, and this one you couldn't even access this heat pump, so the service tech, in order to replace the fan motor, which is behind this, actually cut a hole in the sheetrock there and put a picture over it when he was finished. So he wasn't too happy about that location. One of the things is, what about the heat pump equipment? Is simple or fancy? Do you want simple single speed, or do you want one of these multi-capacity variable speed with extremely high ratings? Now, in the UK, you're stuck with the same rating system that we are, this ISO 13256. Personally, I am very disappointed in this thing because they let people rate in the cooling mode and at temperatures of 59 degrees on the condenser, and the indoor air is at 27. And you get an EER of 53, which the marketing people like to throw out there, and so folks think that they're going to get a 53 EER and it's going to be so great and wonderful, but in fact they don't recognize they will never have these conditions. These machines are also rated at part load, where the conditions are very mild, and you can see here what we have is they rate the machines at part load capacity but with full airflow. So it's a very misleading set of things, and when I try to correct or when I do correct the single speed, the dual capacity, and the variable capacity, this is a line of product of water to air heat pumps. You can see the simple water to air heat pump when you have 86 degree water on the condenser, or 30 degrees C in cooling, and 50 degrees or 10 degrees C in heating, which are more reasonable. You can see that the single speed machines, their average EERs and COPs are improved compared to these more costly fancy things. So you have to be very careful in selecting those things. As they mentioned previously, we do have a rewrite coming out of the book, Ground Source Heat Pumps, available from ASHRAE, and in that we'll include some spreadsheets that will allow you to correct the performance of these machines from the rated conditions, and this is just a screenshot of one of those things. So it's a tool that we try to get to folks to where they don't they use engineering data rather than marketing data to design their systems. Of course, we have this common complaint: they cost too much, and we see with the survey we did. This survey is that 26% of the cost in the we didn't get. Most of the people were very reluctant to give us cost, but of the ones we did, which was about 26% of the cost was the ground loop, and 74% was in the HVAC cost. There was a survey done in 1995 by a very capable group of Canadians, and in that period, since 1995, the cost of the ground loop has gone up a little over 50% in ground source heat pumps, while the cost of the interior portion, the HVAC portion, has gone up, I believe it was 170%. So a much, much greater increase in the interior cost. And this was some of the results. These numbers down here are the ground loop cost Okay, so over here we have dollars right around between 5 or some. This is during the recession. We got some real good prices on ground loops, but you can say $5 to $10 per foot, per square foot of building, and you can see the corresponding number here is about $100 per meter squared of floor area. And then here are the total cost up here of the entire system. So you can see this is the ground loop portion, and these costs up here are the ground loop plus the HVAC cost. See, this is some earlier studies. As I said, the 1995 study, and this was about a 2000 study. So you can see there's much less discrepant, or the ground loop cost back in 95 was a much larger portion of the total cost than it is in the more recent studies. We also use these terms cost per ton, which I've converted to cost per, it should be kW, I think, rather than kW square. Okay, so this is the ground loop cost. I think this is supposed to be kW, and this is the cost of the total system in terms of the capacity of the system. And this was just a cost of the loop for the different, this is in Illinois, Texas, and then this is in Tennessee. So you can see in Texas, it's around the Austin area, that's very, very competitive in terms of loops cost. They do a lot of loops, they do them pretty quick, and so their cost are sometimes, not always, very low. Okay, in summary, I think I'm pretty close to 40 minutes here. Hope I haven't gone too fast. Most of the ground source heat pump systems, which they were all really ground coupled systems that we studied, did very well, with 33% having an E-star above 90 and 61% having a E-star rating of 75 or better. The unitary loops and the one-pipe loops performed very well, and then the central loop ground source heat pumps only performed slightly above the average HVAC system. There were a few that were dysfunctional, had some with energy stars below 50. Basically, a variety of reasons for this. Short loops and dysfunctional controls were biggies, along with some of these VAB systems have huge fans, and of course oversized outside air units that the controls were supposed to control, but ended up not pumping too much outside air in many of these schools. The simple thermostats controls perform better than those with building automation systems. And you do have to remember we were heavily biased toward schools that have limited staff in terms of being able to service these things. As I mentioned to you before, in the school districts that we surveyed, there was on an average, one service HVAC technician for every 5 schools, and some of these schools were huge. Only one of the 14 variable speed ground pumps was working properly. As I mentioned, we had some complaints when the ventilation air equipment size was large. We had a lot of comfort complaints. And as I mentioned before, the inside the building cost was 74% of the total cost of a ground source heat pump system, the HVAC system, and it's gone up 175% since 1995. The average cost of the ground loop was 26% of the total, and the increase has only been 50% since the 95 survey. And the measured data does not show any incidents of widespread overheating of the ground because of long-term performance. Okay, we had no data in this survey where the heating loads were much larger than the cooling loads, so we can't extend that conclusion to the systems where you have much larger heating loads than you do cooling loads, which you might have in the northern parts of Europe. Characteristics, I like to, people say, well, I have a great ground source heat pump system. I query them as, what's your Energy Star rating? It's a relatively inexpensive thing to get, simple thing to get, and so it's nice to know. And a lot of times when I ask folks what their Energy Star rating is, and they go get it, and I don't hear from them again. So it's not a perfect indicator, but it's the best one we have in the U.S. in my opinion right now, for how well a building actually does, as opposed to how well it does under simulations. Most of the ground loop temperatures returning from the loops in these good buildings never got above 90 F or 32 C, and in heating, the loop return temperatures were at least 45, which is 7 degrees C. The loops are long. Most of the better ones had water air heat pumps, and as I mentioned earlier, the piping circuits were individual small central or common loops. Pump control can be on-off rather than variable speed. Loop pump power, 10 horsepower per 100 tons, or not sure exactly what you use in Europe, but I have this subscript kW mechanical or pump power versus 2 kW kW input to per 100 kilowatt of thermal output. We also tend to have non-metallic interior piping, and control tends to be by thermostats. And of course, the people are happy. Both the maintenance personnel and the owners and designers are satisfied when they have a good ground source heat pump system. So I think I'm right at 40 minutes there. I did want to mention this revision. I don't feel like it's commercialism, because Kevin Rafferty and I, the co-author, we don't get any royalties. Original book, basically the University of Alabama subsidized, and this current book that we have a grant to revise it. So we're hoping to have this thing available in late 2014. The revision of this book, which is, I think, sold pretty well for them, and we're doing our best to make everything in international units. So this will be available late in 2014. So with that, I will be quiet and see if there's any questions out there. And not sure which button I'm supposed to push, but
that's great, Steve. It's Ewan here again. Thank you very much for that. That was incredibly interesting and very comprehensive. And I think we've all learnt a lot. And I can tell there's a lot of interest because we've had a lot of questions coming in.
Okay.
So which is a good thing. I think people are paying attention. I had just a very quick question myself, taking the chair's prerogative to ask the first question. Do you have a theory why systems have become more complex? Why didn't the engineers stick to the simple solutions?
It appears that your group, CIBSE, doesn't. Well, my opinion is I'm getting to be a curmudgeon, I've been told, but my opinion is that the way of the world is that a lot of the engineering firms have to advertise and get business, so a lot of the principals are not training their young engineers, and a lot of them have forgot basic engineering principles. So I think too much of what we do comes from the vendors and manufacturers, design information. I think there's too much fallback to people who are selling things. And so that being the case, the more complex above the ground systems would be at an advantage, because so much of the design information and the standards are written with large contributions from vested interest in equipment manufacturers and vendors. I know that's not politically correct, but that's my opinion.
It's a very valid opinion, Steve. It's just interesting. It's interesting that these things happen. Things tend to. You start off with a very simple concept, and then it kind of develops from there, and possibly gets hijacked to some extent. Okay, that was my question. Thank you. Very well answered. We have a number of other questions coming in. We have a truly global audience tonight. We've had contributions from people in Canada, Greece, Ireland, Italy, New Zealand, the UK, and the US. So welcome to you all from around the world. The first question from one of our participants comes from Edmonton in Canada, from David Green. David's question, Steve, is my experience of ground source heat pumps is that the hydronic balancing of the primary and secondary loops is paramount to optimizing performance. And this is something that is not always understood by the contractor, the installer. Is this your experience, Steve?
Yeah, it's very important to on the loop side, because mainly what we deal with primarily in this situation is the water-to-air heat pumps. So I don't have as much experience on the hydronic interior side, but the issue is on the ground loop side is by design you can make these things, I won't say self-balancing, but much easier to balance. And I think that may be one of the reasons why the larger central systems don't do as well, is because they are so much more complex that they're harder to balance. And so what I would advocate is that when you do have a building where you have to have a larger central loop, and there are plenty of those, that you try to break those down into maybe multiple loops. Say rather than having one great big one, have one 4 loops in a building or 6 loops in a building, so that you can have better access to balance in them, rather than try to balance one of these humongous systems.
Okay, thanks, Steve. Okay, that's good. Another question. This is from the UK. It's from Mike Molina, one of our regular contributors. Mike's over in Norfolk, in the UK. Mike is about usability. It is something that's become quite high profile in the UK. Is how the end user experience. So Mike's question was, how have you, Steve, found the end user response following handover? We've had some problems here in the UK with how end users have got on with ground source heat pumps, and heat pumps in general have had a bit of a bad press, should I say that, through user complaints. So what's your experience of that, Steve?
My experience is it's highly dependent upon the quality of the engineer. That's the one thing you saw there, where there was only 3 engineers that did most of those systems that got over a 90, and I think that's the issue, is the design quality. In the U.S., it's rather haphazard of how the engineers are selected. It's like the architect selects them, and oftentimes there's no quality involved in terms of, it's like, is the engineer easy to work with? Does he get things done on time? Not so much as what is his quality. And so the last article in that series of articles in the journal is my suggestion on how to pick a good engineer. And I think if you pick a good engineer, those issues that you bring up will not be as prevalent. But if you pick a bad engineer, you're going to have trouble. So pick a good engineer, and you'll do much better with ground source.
Good. That's a good philosophy for a lot of things in our industry, I think. So it's very good point. Yeah, very good.
Take a look at that. Take a look at that article. It's like architects have in the U.S. they're supposed to give you portfolios, and engineers don't. Why don't engineers give you a portfolio of how well they've done in terms of energy use, customer satisfaction, and cost? It's just something that just makes sense.
Yeah, absolutely. No, absolutely. Thanks for that, Steve. Another question from the UK, from Robin Curtis in Falmouth. He's interested because you were talking a bit about cooling-only systems, or cooling-dominated systems, as probably in your part of the world, Steve. He was saying, what horizontal ground loop or ground loop sizing codes methodology would you recommend? And do you advocate thermal conductivity testing for large horizontal systems?
You know, I actually have an associate, we call him Dr. Dirt, from South Dakota, former retired professor, Dr. Charles Raymond, who has done quite a bit of work in cold climates, and also they've developed thermal conductivity tests. So if you're sizing, I don't know if this is commercialism or whatever, but they do have a program that it's available. The book is available from IGSPA, International Ground Source Heat Pump Association. It's titled Residential Like Commercial Systems, where they do address the horizontals quite a bit more. The testing of horizontal systems, thermal conductivity testing in horizontal systems is problematic because the thermal conductivity varies with quite a bit with rainfall, and so you really should be doing the testing after a drought of 6 months to get the design conditions, and you can't always do that. So it's much more problematic, and that's why in the horizontal systems it's just good to have a lot of field data of load versus operating temperatures in the loops. So I don't really recommend horizontal testing other than just simply figuring out what's down there in terms of the geology, sand, clay, and that sort of stuff, where you can estimate the conductivity, but it's very hard to predict with a test. Okay.
Okay, thanks, Steve. We've just lost
Okay.
Ewan there, I think. You back, Ewan?
Did you hear my answer?
Sorry, no, I missed that. I don't know. I don't know if everybody else heard. So yeah. I think
we heard. Okay, that was great.
Okay.
Okay, so you got Costas's question. Okay.
Okay.
We've got Amir Rezai in Denver asking, do you have any recommendations for someone who's involved with modeling ground source heat pumps? And also he asks about payback. Do you have comparison of payback periods between complex systems and the more simple systems?
We weren't able to get anybody with these complex systems to give us any numbers. I think they were rather embarrassed because they knew we were going to publish stuff, but we were not able to get any information. The other thing is the models that are out there are computer models, and I think there needs to be a lot of work done in this area, because most of the models simply look at the Earth as a solid, a conduction solid, and they don't take into the fact that when you're in cooling, when you raise the temperature of the Earth loop, you also change the vapor pressure of the moisture that's in the soil, and it will evaporate. And the models do not take that into account, okay? And it's significant. It's probably one of the reasons why the models are over-predicting long-term temperature change, is that you can take a reduction. This is just a number that I put together. A reduction in the moisture content, the heat required to reduce the moisture content 1%, say from 15 to 14% moisture by weight. That amount of heat is the same as the amount of heat required to raise the ground temperature 30 degrees. It's huge. So the Earth can become a huge cooling tower to some extent. It's just that it's very, very difficult to predict the recharge and how much that occurs. So the modeling the ground is something that needs to be informed by measured data, and we don't have a lot of measured data. So not really big on ground modeling right now. I think we've got a lot to do.
That might be interesting, Steve, in light of the next question, which is from David Green again. David was in Canada, asking about how efficient ground source heat pumps are when the average winter temperature falls below minus 15 degrees C.
In the ground loop?
Yes, I guess he's talking about ground. Yeah, he's talking about ground temperature, I think.
Yeah, it's.
Well, no, he's talking about the average temperature in a cold climate, so minus 15 degrees must be the ambient, I guess.
The ambient. Well, again, it depends on the size of the ground loop. If you look at that screen I had up there, you can put that number in that screen. There is a predictor. So in other words, you put everything in that screen. I don't really, not sure how to distribute that, but it will be part of the update.